All right, hello. Welcome to the Off by One Security stream on Friday, March 14th. I'm joined today with Josh Reynolds from Invoke RE. Give it a moment here. Just again, I always say this, it takes a while for all the platforms to connect when we start up a stream. But this, of course, will be on YouTube afterward if you miss any of it. But I guess if you heard me say that, then you're probably not missing any of it, but in case you leave early. But all right, let's go ahead and start. The topic for today is Deobfuscating Golang with Binary Ninja. Josh, why don't you give a little background about yourself and so folks know who you are who don't?
Yeah, for sure. So my name is Josh Reynolds. I work for a company called Invoke RE, which I founded about 2 years ago now. More recently, prior to that, I was working for a large Intel shop at a EDR vendor that is quite important and pretty integral into many different security technologies, which you can probably guess who that is. And then before that, I was working at Cisco. And during that entire time, I've basically been doing primarily malware reverse engineering and specializing in malware efficacy of security products. So today, I just wanted to go over, like the title says, reverse engineering Golang, specifically with Binary Ninja, and going over a specific obfuscator that's being used to obfuscate Golang in order to make that reverse engineering harder.
Cool. Yeah, we were just talking recently on a stream about some of the, especially on the .NET, C#.NET side, like obfuscate, was it Confuser EX? That's what it's called. The one in particular I was thinking of. It's pretty insane how much those things can scramble things around and slow you down. But luckily for that one, there was a open source deobfuscator. But I imagine that not every obfuscation tool is going to have a friendly counterpart that helps us deobfuscate things. What percentage of malware, I guess, would you say are you seeing in Go? Is it growing? Is it more common these days?
Yeah, it's definitely a lot more common, I think, because of its ease of use. So we find that there's a large number of different malware groups that are leveraging Golang primarily because it's cross-platform as well. So if there's like, say you have, I don't know, a piece of malware that you want to run on Windows, Mac, Linux, different Unix variants, then it's really good because you can just cross-compile it with various compiler flags. Also, as I mentioned, it's pretty easy to implement these different types of malicious operations in Golang. So I don't know an exact percentage, but I would say probably maybe around like 20% of what I reverse engineer these days is implemented in Go. And obviously there's a huge uptick in these third generation languages, things like Rust and Go and .NET, specifically with C#, that we're seeing being used more often now because, again, their ease of use and it's more accessible. Rust has a little bit more of a learning curve, but it's definitely being more used now since it's a system programming language, and it is pretty good for writing malware.
Yeah, great. So a lot of people have been asking for more malware analysis sessions. So happy to have you here. I think what was I going to say? Some of the other things are around malware on the Mac OS side. I'm told that we don't do enough Mac OS stuff, but I guess if we're looking at malware like this, it applies to all the different operating systems. So cool. Well, I know you got a lot to go through. If you want to, I think you said you had a few slides to go through and then some demonstrations and all. I encourage everyone, of course, as usual, to ask questions if you do have them. I'll interject, of course, if it's related to what's being covered at that moment in time. If it's something more generic, like what do we think AI is going to do to this world of cybersecurity, we'll save that to the end and the more philosophical stuff. But yeah, if you want to go ahead and share your slides, we can get started.
Yeah, for sure. So I'll share my screen here.
And I've learned for folks watching or listening to always ask in advance to make sure the font and everything is big enough on the screen, but it's the case where you can't see something, just let us know and we will get that enlarged.
All right,
cool.
Yeah, should be good to go.
Yep, looks good.
Perfect. All right, so yeah, as I mentioned, wanted to go over a project that I've been working on called Ungarble today. And that works with Binary Ninja. So we're going to be looking at deobfuscating malware with Binary Ninja using this project that I wrote. So first and foremost, let's just go over the current state of reverse engineering Golang. So more often than not, when you open a Golang binary, especially if it's malware, it'll be stripped of symbols. And that's just by doing a release build. So it's pretty standard and not too difficult to do. However, because of the way that Go operates, it actually has embedded structures that can be parsed in order to extract information that is used at runtime that can be applied back to your reverse engineering database. And it makes it a lot easier to reverse engineer. So one of those structures is called the PCLN tab, or the program counter line table. And that's used to hold, like I said, a bunch of different runtime information, things like function names, the information that's needed to get stack traces, etc. So that's a super valuable structure that can be parsed and used to extract runtime information that can be applied back to the database. And then there's also different structures like the module data information, and a tool that we'll be looking at today called GoResim will actually extract this out for you, and then you can apply it to your reverse engineering database. Some other techniques that are used for reverse engineering Go nowadays is setting the correct calling convention. So more often than not, in tools like Binary Ninja, Ghidra, and IDA, they will not be able to guess the correct calling convention for Golang simply because it is non-standard. And obviously there's a whole bunch of complexities and nuance under the hood for how they're deciding what calling convention to provide for a specific function. But typically there's tools for Golang now that can be used to apply the correct calling convention for functions, which can then be used to recover the correct amount of arguments and number of returned values. And then also there's string fix-ups that are often used by different tools for reverse engineering platforms. So unlike C and C++ and other common languages that you might be reverse engineering or that are compiled into binaries that you might be reverse engineering, the strings in Golang are not delimited by null bytes. So this actually results in a whole bunch of strings that are just in single string blobs, and those are referenced at various offsets throughout the binary. So this has been solved by, I believe, Binary Ninja, not the delimiting part, by getting the correct offset. And then there's other tools that just help with finding the end of those strings. So because of the way Golang works, it actually has the length of that string in addition to the pointer to that offset. So if you can recover those two values, you can recover those strings effectively and apply them to your reverse engineering database. So there's been these developments that have happened over time simply because of the complexities of Golang. There is a large amount of statically linked functions and information that results in a huge binary that you need to reverse engineer. But there are techniques that can be used, such as these, in order to assist with that process. So for those of you who are not aware, obfuscation refers to the deliberate use of techniques to make malware more difficult to understand, analyze, and detect. And the goal of obfuscation is to hide the true purpose and behavior of the malware while also inhibiting static and dynamic analysis by reverse engineers. So essentially, obfuscation is just techniques that are used by malware authors, red team tool authors, to make reverse engineering more difficult. And that can be either in the code itself, or it can be techniques that are applied after the fact in order to make things more difficult. So for example, you might XOR a string that is being used at runtime in order for that string not to be visible by the reverse engineer. But then you have, say, compile time obfuscation techniques, such as the ones that we'll be looking at today, that will actually be applied after the source code is compiled or during the compilation process and linking process. And there's other projects that are doing this, like with the LLVM compiler. They have situations where they can take the LLVM lifted code and then apply obfuscations at that point in time, just as an example. So a project that we're going to be looking at today is called Garble. And this is specifically geared towards Golang projects where it can be used to replace a whole bunch of useful information in those Golang binaries, i.e. those projects that and techniques that I mentioned earlier, this is a project that will attempt to remove as much of that information as possible in order for it to be more difficult to reverse engineer. So for example, it will replace identifiers, package paths, file names, etc., with these hashes of those values, and then it will base64 encode those as well. And since the hashing algorithms are one-way functions, you cannot recover that information when you're reverse engineering them. It will also remove a bunch of build information, module information, debugging information, and the symbol table. So that cannot be used to recover information about the given Golang binary. And then it'll also be used to obfuscate literals, so in the sense of Golang, a type of literal is a string, and strings are very useful during the reverse engineering process as they let you identify specific types of information and potentially the type of function being used. And especially when functions are statically linked, then you can use those strings to identify those functions potentially, etc. So what we'll be focusing on today is recovering those string literals, because it'll give us a large amount of information about the binary that we're going to be reverse engineering. So why do you care, right? So the reason I looked at this initially, and it's kind of a funny story because I was doing a live stream at the time, is because I was doing a live stream series on analyzing the red team tools that were publicly accessible, so open source red team tools. And during that stream, I compiled Sliver, which is a common C2 framework written in Golang. And at the time, I had not looked at compiled versions of Sliver. I just looked at the source code. And I'd reverse engineered Golang in the past, and I thought, this is going to be a breeze. I've looked at a lot of Golang malware. I've reverse engineered a lot of different projects, but what I found was that they were using this obfuscator. And when I opened it on this live stream, having not looked at it before, I was like, uh-oh, like I'm not going to be able to get through this on stream simply because of how obfuscated this code is. So again, it's being used by a bunch of different real world malware variants and these red team projects to make RE a lot harder. And if we're able to, as I mentioned, if we're able to recover these strings, then we can recover a large amount of built-in functions that are used by Golang, and we can make our reverse engineering process a lot simpler. So maybe we can pause for questions there before I get into
I got a couple questions on Discord. Let me see, go back over there real quickly. One question, and you might be getting into some of this stuff, so if you're going to cover it, just say that. But how are malware authors handling cross compilation for different architectures with Go?
So with Go, it's pretty simple, I believe, for most different platforms. So actually, I can show you an example because I was going to do one today. So since I was primarily looking at Microsoft Windows binaries and I'm running a Mac OS operating system right now, I needed to compile the example binaries that I'm going to show you with the flags that are needed for Microsoft Windows. So if I go to build non-garbled, then literally all you have to do in Golang is set the environment variables for a specific operating system and architecture. So in this instance, I want to compile this binary for Microsoft Windows, and then I want to compile it for AMD 64 or an x86 64-bit architecture. And then I simply call go build on the command line in order to build for that operating system. So similarly, if you wanted to build for Mac OS, or if you wanted to build for Linux or different types of operating systems, you would simply have to set those flags. So it's pretty straightforward.
Nice. Yeah, another one is how are malware authors dealing with Go routine-based concurrency to evade analysis?
So if I understood the question correctly, so they do leverage concurrency with Go routines, etc. And they are using that to, say you have like a command and control thread that you want polling the command and control server while conducting various operations. They'll implement those Go routines in order to conduct those various operations simultaneously. And having those Go routines or multi-threading in place, that's effectively multi-threading under the hood, it actually makes it quite a bit harder to debug it live, because if you set a breakpoint, for example, it might hit one thread while you're debugging another thread, etc. So it actually makes it quite a big pain. So what I usually try to do in order to avoid that is simply do static analysis primarily, in order to avoid doing any dynamic analysis if they are leveraging concurrency in Go routines. But having also written quite a bit of Go, Go routines are quite nice for doing those multi-threaded operations. Having also written things like Python, which are not good at doing concurrency and multi-threading.
Cool. There's one more. I'll ask this one. It feels like this one's written like a test question. How are malware authors handling memory management in Golang to avoid detection, such as reflective DLL loading and in-memory execution?
So I do think the binary size is a large issue when writing, say you're a red teamer and you want to write an implant or whatever. I do think the size of the binaries is quite a large issue, and I don't know how much. So like there are operations that you can do in Garble, for example, that will strip as much information as possible to make the binary a lot smaller. But because of how the Go runtime works, it's very difficult to remove all of that information and make it like as small as, say, like a C binary. So I do think that, I don't think that's an inhibiting factor for security technology detection, but I do think it could be a red flag, say if a piece of malware was using Golang over something smaller like C or C++. But because of the complexity and the size of the binaries, that actually kind of works to the advantage sometimes of a lot of these security technologies. Like they won't, some AVs, for example, won't scan certain files of certain size if you make them large enough. Like I can't remember what the project was called, but it was some red team tool that they released at DEF CON, a couple of folks, and they're producing like 20 megabyte binaries. So a lot of AVs won't scan the entire binary, or they won't try and run the entire binary simply because of its size. So I think it can kind of flip flop where the memory footprint's higher, but the on disk size can sometimes benefit the malware operators.
Cool. It's funny. Somebody in Discord asked, why don't malware authors utilize more encryption versus obfuscation? It made me think of an old Microsoft article. They did this great analogy. I'll probably mess it up, but they said something like encryption is like if you were bringing your lunch to work and you had 6 different items. You've got your soda, and you've got your sandwich, and you've got the cheese on the sandwich, and you've got yogurt or whatever, all the things. And you lock it in a box and you take it to work. No one knows what's in there, but you do at some point have to open it with a key, and then all the ingredients are in there. And they said obfuscation was more like taking a blender, putting all the things in a blender, turning it into some brown muck, and taking it to work. Like you're still getting the same nutrients, but no one knows what the hell you're eating. So I thought that was an interesting analogy.
Yeah, I do like that analogy. Like for what we're going to be looking at today, it would be like having a separate blender for every string. So it made analyzing or reverse engineering that obfuscation pretty difficult.
I'll post this last one up. Can you see the question on the screen I just posted?
Yes. Will this content be more relevant from now on, since TypeScript's team porting the TypeScript compiler and tools to Golang? I don't know if I've seen any malware leveraging TypeScript. That is a good question, but I could see somebody leveraging TypeScript and then obfuscating the TypeScript runtime under the hood to make it more difficult if it's going to be open source. I would assume the TypeScript runtime would be open sourced as well, but yeah, I don't know how relevant that is to exactly what we're looking at today, but it's a good question. I also read about the TypeScript stuff.
Cool. All right, well, carry on.
Cool. Yeah. So I just wanted to show you a few different things because we're going to be looking at a few different tools. So first and foremost, let's just look at an example of what Garble does. So here I just have a very basic Golang program that will just print out a string. And so it's just doing print line, garble, garble, garble. So again, this kind of demonstrates the ease of use of Golang. We just have one format import, and then it's using the format library in order to use the print line there to print out that string. And then if we were to just compile this normally, so again, I'm going to run that, if I can type, I'm going to run that build non-garbled, which will just build it using the regular Go compiler. And then once I do that, we have test2.exe. And then if I run strings on test2 and we look at the strings, then one, we're going to have a whole bunch of different embedded information, I guess later on. But more importantly, I'm going to have that garble, garble, garble string, right? So as we'll see in Binja, it's a little bit more evident. So if I open this binary in Binja, I already have this kind of pre-cooked because I didn't want to wait for Binja to process all these things because they are large binaries. If we want to see how large that one is that I just created, test2.exe, it's 2.1 megs. So for like any reverse engineering platform, it's going to take a little bit to analyze. But again, I did this ahead of time. So if we take a look at our test2 function here, in Golang, you have, if we could look on the left-hand side here, we can see because this is a normal build, I haven't stripped any of the strings, etc. Binja was able to actually give us a whole bunch of different function names. And as you can see, like I mentioned earlier, Golang embeds a whole bunch of different statically linked functions into the resulting binary. So let's scroll down here. So even though it was literally just like a hello world binary, essentially, it embeds all of this runtime stuff into it. So this is what makes reverse engineering Golang a little bit harder than say C or C++, simply because they don't do a lot of dynamic linking. It's all static linking. But fortunately, because of the embedded type information, embedded strings, string table, etc., we're able to recover these function names. So in every Golang binary, there's going to be a main.main. So this is just the main function within the main package of our Golang binary here. And then we have that format print line here. So as you can see, this function name is marked up for us, and a little bit of weird pointer results in the decompiler here. But if I double click on this global variable, we can see that this is indeed our garble, garble, garble string. And then that's passed to our format print line call here. So say we wanted to see how Garble works and how it makes reverse engineering Golang binaries a lot more difficult, then I would just run. So I've actually modified the Garble project itself in order to show this to us. But how Garble works, actually, I'm just going to show the source code before I get into how I'm going to build this. But so how this is actually the Garble project source code. So I didn't mention it earlier, but I should have, that this is a fully open source project. So this is accessible to anyone, which is why it's being, I think, leveraged by so many folks, because you can see the code and how it works, as are many different GitHub projects. So if we look at the AST calls here, so how this works is, let's see. They're using this Go AST package, and this actually allows them to parse the syntax trees of the Go code that is being compiled. And then using that package, they're able to interpret and obfuscate the Golang code itself prior to being compiled. So if I go to, there should be an obfuscate function in this main function here. Sorry, I should have had this up earlier. Let's go from here. and it applies a much different transform. So if I go down here more, then we can see it's probably not the best keyword to use. Let's see. Sorry, guys. Hold on, 2 secs. Let's try transform. Okay, so yeah, so this will basically get all of the linker variable strings. It will generate an off-rand object. This is used by the obfuscator transform. And then it will basically read the source files, and then it will look for, using the AST of the Golang source file, it will actually find all relevant types. So for example, those string literals, it'll basically walk the AST, and then it will actually acquire the relevant parts of the source files and then transform them using various obfuscation routines. So instead of just walking through the source code, which is boring here, let me show you the actual output of this. So if I go to, again, main.go is just that print file or print line. And then if I compile it using my little script here, so in build.sh, I'm going to be calling, again, those environment variables, not calling, but setting those environment variables. And then I'm going to execute Garble with the literals flag. So this will actually build the current Golang project, and then it's going to obfuscate all of those string literals. So it's going to replace those string literals with obfuscated versions of themselves. So if I do build.
Is there much around control flow modification?
So they actually do have control flow modification. Fortunately, a lot of folks who are leveraging Garble currently aren't using that, but I'm hoping that they don't, but maybe after seeing this stream, they will. But yeah, for the control flow obfuscation, they do have to integrate some pieces of Garble inline into their source code base. So I'm guessing that's why they haven't used it yet, but that could be a big pain.
Yeah, I asked because someone was asking around whether or not Garble will modify the machine code itself, or is it more just around like encrypting things and renaming symbols and all that?
Yeah, so by walking the AST and then replacing the code itself with obfuscated versions of that code, then it's actually modifying the source code itself. So it's using that package's ability to understand the Golang source code to find the things that they want to obfuscate, and then they obfuscate them, if that makes sense.
Yep.
So this kind of looks weird, but this is actually the obfuscated version of our simple print line program. So here they've replaced the format with this package. And then you can see here that they've created 2 things. So they have a key array here, or a key slice, that is these bytes. And then those bytes are being used within this for loop as this key within a range. And then they also have another byte slice, which is this data, and that's also being used in this for loop. So this is a really basic form of obfuscation that they're using. They have a whole bunch of different types of obfuscation routines. One's like a subtraction, one's a XOR, one's an add, which is the case here. And what they're doing in this case is just a simple add. But if I was to change that source code a little bit, say we add one more Garble, and we build it again, then this gets a lot more complicated, right? So we have our main function here. Now the decryption key is like 220 bytes. And then we have a full case statement. We have a counter. We have an XOR on each iteration of that for loop. And then within this case statement, we have various pieces of data being appended to the data slice, and then again, that loop continues to iterate. So the reason that I had to take the approach that I will be discussing next with Garble is because not only does it pseudo-randomly choose the types of obfuscation algorithms that it's going to be using for each string literal, but it also inlines a lot of that code into the source code itself. So you can't really tell in this example because it's simply one string that's being obfuscated, but it will actually modify the original literals for every single embedded Golang package. So not only is it modifying not only is it obfuscating the source code for our main function here, but it's also obfuscating every single other statically linked package. So it makes it pretty difficult to understand. So if I go, so now that you can kind of see how it transforms a given source file, let's look at it from a compiled binary perspective back in Binary Ninja. So if I go to test garbled here, we can see one of these obfuscated routines here. And this is how this looks in the decompiled version. So on the left-hand side here, I have the disassembly. So this results in some pretty ugly looking disassembly where we have these keywords that are being assigned into these general purpose registers. And then those are being assigned onto the stack. And then those stack operations continue at various offsets on the stack, which are relative to these local variables. And then we have the deobfuscation routine down here. If I go into GraphView, it's a little bit easier to see how this looks in the disassembly. But basically what this deobfuscation routine is doing is it's looping and then performing this XOR, and then that XOR is done with these various keywords. And then if we look on the right-hand side here, the decompiler in Binary Ninja actually has the ability to fold a lot of these things into these literals, or these, sorry, not literals, into these synthetic functions. So for example, built-in string copies being what's used here to represent this string that's simply that byte array that was being copied. And then we have a built-in mem copy that's also being used. So again, this is all folded and lifted into this high-level intermediate language decompilation format. But as you can see here, we have a full while loop that's basically looking for, this is the length of the string being deobfuscated. And then there's that XOR operation that's occurring here. So in this specific string example, this full deobfuscation routine is being done for one string that's hex 12 bytes in length. So hopefully that makes sense. So, and then as you may have noticed on the left-hand side here, we have literally no function names. And that's because they were stripped by Garble. And then not only were they stripped, but they were also replaced with those base64 hashes that I was talking about earlier. So if I go to that Go Resim tool I was talking about, so this is a great project. I could probably go to the GitHub actually real quick. Go Resim. And so this is actually from the Mandiant Flare team, who is now Google Cloud. And this will extract all of those this will extract information from all those structures that I was talking about in my little presentation. So the PCLN tab, the module data, etc. And then it'll provide that back to us. So even though this is the information is stripped out of this binary and then Binary Ninja can't automatically apply it, it actually has the ability to recover some of that information. So say we said, okay, so since I didn't get any function names in Binary Ninja, I'm going to use Go Resim. Then I do that with our test2 garbled. We can see here that, so this results in a JSON file that gives us the package names and then full function names here. And as you can see, it's just gobbledygook, right? So it will actually still embed these package names because they're needed by the Golang runtime, but it will modify those accordingly. So if we wanted to see that in action, again, by the Garble compiler. I can actually do Garble, and then I'll do dash literals again, build, and then I believe it's just dash debug. So this actually shows us that these hash operations occurring within each package and the resulting package name. So some of you might be asking, well, can I reverse this in terms of being able to recover these function names accordingly? So Garble does have that functionality embedded, but that you need a seed value. And that seed value is pseudo-randomly generated and is cryptographically secure. So they're using the built-in random library from Golang, and that is indeed cryptographically secure. So that was one of the first things I looked at. I was like, okay, so if they're generating a seed, is it possible to recover that seed and then possibly recover this type of information? But unfortunately, it's not. So what I ended up doing was, when I was doing all this research, I ended up seeing these different patterns that made me think it might have been possible to potentially capture some of these obfuscation sequences in Golang or in Binary Ninja that are produced by Golang, and then exploit those. So as we can see here in this particular loop, there is a sub. So it's creating room on the stack, and then it's moving a bunch of these keywords into those local variables that I mentioned earlier. And then there's this loop. And as we can see at the end of this loop, there's if we look on the right-hand side here, again, if we have that while true and RAX is greater than or equal to hex 12, then we call this function. So if I highlight that function, we can see that it's called in a whole bunch of different places. So why would a specific function be called throughout the binary in a whole bunch of different places? So it turns out, based on how Garble operates, it uses the runtime slice byte to string function. So this will actually convert all the byte slices that it's performing these deobfuscation sequences on back into a string by calling the exact same Golang function every single time it deobfuscates a string. So that was another pattern that I observed, and I was like, okay, cool. So because of how the way Golang works, we can actually exploit that fact. And then if we see a call to this runtime slice byte to string, we can potentially recover all of the strings that way. So I know I covered just a bunch of ground. So does anybody have any questions?
I just posted a few questions from Discord. I'll pop it up so you can read them. I'll read it out loud too for folks who might just be listening and not watching. But the question is, are attackers using Go's unsafe package to manipulate memory and bypass certain detection mechanisms?
Yeah, absolutely. So if you like, a really good example is the Sliver project. So they do a lot of, let's see. I think they do a lot of unsafe stuff. Maybe I won't go through this code on stream just because I don't know its structure, but yeah, I would take a look at Sliver because they're definitely doing a lot of low level interfacing and loading shellcode and stuff like that. So that might be a good example to look at. But yeah, they're definitely leveraging the unsafe functions in order to either call C code or do various unsafe operations with the Windows operating system in order to achieve their objectives.
Cool. Here is another one is, are you seeing much use of Go's reflect package to implement dynamic function calls and obfuscate execution paths?
So I actually don't see a ton of reflect being used myself. For the most part, a lot of the malware I've looked at is fairly rudimentary in that they're just leveraging most of the standard packages. But again, I'm sure more of these advanced projects like Sliver, for example, are using reflect. But I would have to double check. Off the cuff, I don't know of a ton of use of reflection from what I've seen.
Nice. These 3 questions are from the same person who clearly knows Go pretty well.
Yeah.
Are attackers using opaque predicates or other control flow flattening techniques to complicate decompilation?
Yeah, so Sliver, or not Sliver, Garble actually has that. So if I go into their docs, we talked about this a little bit earlier, but so they have control flow obfuscation, and I do know that they have control flow flattening. So yeah, this is like a direct example of what you're wondering about. I don't know if they have opaque predicates. That's a good question. I don't believe they currently have opaque predicates, but I'd assume if they can implement control flow flattening, they'd be able to implement opaque predicates. But I haven't really seen them being used actively in the wild myself, to be honest.
And a good definition for opaque predicate would be something like maybe the intention being known to the developer, but not to someone reversing it, right? Is that what you would say?
Yeah, like a practical example of that would be, in order for a specific branch in the code to be taken, a certain condition would have to be met prior to that occurring. So what more often than not, what you'll see in a lot of malware is a arithmetic operation occurring prior to a certain condition being met. So it makes visualizing the control flow a lot more difficult, simply because you would have to do some form of solution for that opaque predicate in order to understand exactly which branch it was taking, etc., in like an if statement or whatever.
Nice.
All right. Great questions. Keep them coming. Questions are always good. So, okay. So after I saw that this slice byte to string was being called in each instance that these literals were obfuscated, I basically just wrote a heuristic within this plugin that I wrote for Binary Ninja called Ungarble that would basically look for similar sequences to these keyword assignments, etc., and then a call after the fact in order to identify potential locations of this runtime slice byte to string. I'll just change the name of this so I'm not slice byte to string, in order to identify the potential location of runtime slice byte to string. And the way I would do that is basically just look for these obfuscation sequences. So I can access these disassembled operations in Binary Ninja using their Binary Ninja Python API, which is really good, which is why I primarily did this in Binary Ninja and not something like IDA, because their API is quite a bit harder to use. And then once I was able to find this obfuscation sequence, I basically walked the basic blocks in a recursive fashion to look for the outgoing branches from the given obfuscated block until I found a block that looked like it was probably a call to runtime slice byte to string. And then once I was able to find the call to runtime slice byte to string, I basically used all the cross references. So when I highlight this on the left-hand side, you can see those here. I basically used all the cross references to runtime.slicebyte to string to find potential obfuscated locations. So not all of these are indeed obfuscated locations. So there is a heuristic that I had to use in order to determine, okay, is this actually something we want to try and emulate? Spoiler, that's how we actually recover the strings, is through emulation. But once I'm able to identify, sorry, Binge is being slow here. It's probably just because of the stream. Once I'm able to identify locations that are highly likely obfuscated locations, then I basically work backward. Let's see if I can find a good example here. Let's just go back to the original example because it was pretty easy to visualize. Then I would basically work backward from the given basic block that runtime slice byte to string was being called in. And then I would walk back up the basic blocks until I found a series of operations that looked like they were probably doing some form of obfuscation. So TLDR basically would look for the obfuscation sequence leading to an unknown function, which could be runtime to slice byte to string. Once I found that, then I would basically look at all the cross references with that throughout the binary and then try and find more obfuscated locations from there. And then once I was able to find both of those things, then I would basically get the start and end address of these locations, and then I would emulate those instructions. So for those of you who are not aware, there is a project that's basically used by everybody now called Unicorn, that is essentially a stripped down version of QEMU or QEMU, however you want to pronounce that. And Unicorn is used in order to emulate a given architecture's instructions. And it's not actually executing those instructions. It's simply implementing a virtual machine, or what you can think of as a virtual machine. And those instructions are executed within that virtual environment. So Unicorn is really useful simply because it's super lightweight. Like you can spin up a Unicorn virtual environment in milliseconds, and then you can use that to execute a given series of instructions. And then you can have an emulated stack. You can have emulated data structures that you would have running if this malware was actually running in memory. And then you can monitor the execution of those emulated instructions. So why that's useful is, say I wanted to execute this deobfuscation sequence without having to actually run the malware, I could simply capture these. So if I go back out of graph view, we can see the opcodes here. I can actually capture these opcodes and then emulate them. So I didn't really want to write another Unicorn wrapper. A lot of folks who are doing reverse engineering know that there's a whole bunch of different Unicorn wrappers. So I actually used what was called, or this is a submodule of a project that a friend of mine maintains called Binary Refinery. So this is from Jesko Houtenheim. And this is what's known as kind of the command line version of CyberChef. So for those of you who are not aware, CyberChef is a really cool project that you can basically use to transform given sets of data using various compression or encryption or encoding algorithms. And that's really useful for doing malware analysis because a lot of standard algorithms and standard transformation algorithms are used by malware, whether that be during the deobfuscation process or when they're encrypting or encoding information to send away or store information, etc. And binary refinery is effectively the command line version of that. So what's really cool about binary refinery is you can essentially pipe given information to various, let's see if I can make this a little bit bigger. You can pipe various information to various modules that he calls units, and these units can perform those whatever given transformation that is. So in this example, you have like emit 7zip xt7z, which will basically do the 7z decompression, I believe. Okay, this is a dependency example. I'm going to show you how to use this. But yeah, like here you have emit, which will basically just do a print. Then you have hello world, hex-r, which is going to encode that, I believe, and then do these various units. I don't remember what ZL is, but that's okay. And then it'll do base64 encoding. Here you have basic units that will do things like carving. So you can do really useful things like give me the longest base64 string from a file, and then do the base64 unit on that in order to decode that base64 and then dump it to a file using the dump unit. So it's really useful for basically transforming various pieces of data. But what we're going to use it for is actually, let's see if I can find the docs from here. I might have to go to the website, which is fine. Oh, that's not it. Hold on 2 secs here. Here we go. Okay, so binref.github.io if you want to follow along and take a look at the docs. if we go down here, there's a unit called vstack. And this will actually basically do what we're talking about, but it'll do a whole lot of heavy lifting for us. So what's cool about this unit is you can do it to, or you can take a given portable executable, which is the executable format that we're currently reverse engineering. It will map that into memory. And this is all within the Unicorn virtual address space, right? This is all the emulated little virtual machine that I was talking about earlier. And then we can emulate between given virtual addresses. So if we go back to Binary Ninja here, these are actually virtual addresses within Binary Ninja that you can, that would effectively be the virtual addresses as if the portable executable was mapped into memory. So say we wanted to emulate a given sequence with this vstack unit with Unicorn with two different virtual addresses. I can show you how easy this is. So I have my virtual environment here already set up for Python. And then I can do something like vstack, or sorry, I have to do emit. So this will actually read that file. And then I can do vstack, and then -s is the end address. So I'm going to get the start address first. So say we wanted to emulate from here. And then stop at the call to slice byte to string. Then we can do that. And let me do the verbose output here. So how vstack works is, the reason it's called vstack is because basically what it will do is it will monitor for operations that are occurring on the virtual stack. So because of how these instructions work, they are all performed on the stack. So as we saw in that initial setup here, all those keywords are being written to the stack. And then every single time one of those XOR operations occurs in this EDX, then it's actually written to, let me see, where's the right operation? On each one of these loops, it's actually written back to the stack. So because of how that works, this is where the write operations are occurring after the XOR. But because of how that works, vstack will actually monitor for those write operations, and then we can actually capture those using another unit. So here it was pretty clean, but this is basically the output of the vstack unit, and these are actually all of the resulting stack operations that are occurring from our emulation sequence. And the string that was deobfuscated, not too exciting. This is, in this instance, text file busy. So this is just from some embedded Golang that was embedded within our binary here, our test binary. But so any questions on how vstack works, how any of those things so far?
No, not on that. Just someone saying they didn't know Refinery could do that. So that's good. That's really cool stuff. I like it.
Yeah. Yeah, really cool. Shout out Yesko. Definitely one of the best projects for probably really good for CTFs, whatever.
Yeah. Someone did post a question on, I knew this question was coming. It was just a matter of time because it comes up on every single stream. How do you, like, they're specifically calling out like what you just did, saying, how do you see AI affecting the malware analysis job market? Do you think it'll be an aid to analysts or a full replacement?
Yeah, so currently I've been using it quite a bit. For my day-to-day, I've been trying to kind of stay ahead of the curve. For Binary Ninja specifically, they actually have a plugin called Sidekick. So if you check out our YouTube, I should have actually given this to you earlier. It's just at invoke reversing. Then I do have a video on this, but they basically have integrated a plugin into Binary Ninja that leverages large language models in order to assist with the reverse engineering process. It's not mature enough to the point that it's actually replacing a lot of those processes, but it's definitely very helpful in being able to understand the binary quickly and identifying interesting parts of the binary, which is a large part of the malware reverse engineering process. So personally, I think they're probably the most mature project for doing that. I've seen a lot of different plugins for various reverse engineering platforms that are leveraging it. I don't really see it taking my job anytime soon, but it's definitely something I'm aware of and I'm trying to leverage and stay at the forefront of. But it's definitely very useful. But yeah, I wouldn't say it's going to take my job anytime soon. Large language models aren't perfect. They hallucinate all the time. They produce imperfect results, but I am seeing some pretty interesting improvements. Like I had some obfuscated code the other day and I threw it into a large language model and it fully deobfuscated it for me. I think it was like PowerShell, which I was very surprised of because it's like basically stack transformers. And I think they're probably getting to the point where they're a lot more advanced than what's publicly known. But that was pretty surprising to me. So pretty interesting.
Yeah, I think a lot of people, especially the folks newer to the market, are worried because those tasks that someone can do when they're first starting out and interning and all that will more likely be something that can be automated and replaced versus those with advanced knowledge of this stuff. And like you said, keeping in the forefront and everything. I think that's the biggest point, is making sure, and I say this all the time, just never become complacent, stay at the forefront, use it daily, and you should be good.
Yeah.
Hackers Vibes is asking, do you know any CTF challenges based on Go, or where can I practice malware analysis? Any resources you would recommend for learning this stuff?
Yeah, so for CTF challenges in Go, I'm sure if you Google like CTF challenge in Go, you can find some. I know that's not a great answer, but if you're interested in learning malware analysis, plug, we do malware analysis training on the InvokeRE website. We don't have any modules on Go yet, but that's definitely something coming in the future. There's a ton of resources for learning malware analysis online that are free. Like on our YouTube channel, we have a ton of stuff. On various other YouTube channels, there's tons of stuff. OA Labs, plug for them. Shout out Sergey and Sean. They do a lot of really good stuff. I know Sergey's been on this stream as well. So yeah, definitely those are the things that are top of mind. Cool. Huntress CTF has some Go challenges. There you go.
All right, I'm just gonna post that link up to your YouTube. Cool.
Sweet. Awesome. Thanks.
Yeah, I posted CTF Time. That's a great site that lists pretty much all the CTFs out there happening. It's fantastic resource. Same thing with CFP Time. CFP Time is a call for papers. Shows you every conference and the due dates for the papers. That's another good spot.
Nice. I didn't even know that existed. That's cool. Yeah. All right, cool. Yeah, let's keep going. So basically this is all to say that I wrote Ungarble, and I can kind of show you what that looks like. I don't really have to show you the code anymore. Basically, it just does recursion from those basic blocks that I mentioned. So if we go up here, basically it will look for slice byte to string sequence. So this is using a whole bunch of kind of nested lists, which isn't great in Python, but basically it'll get the disassembly operations. It'll look for the sizes of those operations. And then I have some examples here of other formats that it'll look like for call sites to slice byte to string. And then I have some more strict versions of those as well, because I was getting some false positives. And then once I find, these are the recursive steps. So once I find those, then using the Binary Ninja Python API, you can actually do like basic block outgoing edges. Then you can walk the outgoing edges of a given basic block, and then you can walk those recursively, etc. So that's basically all of this is on the InvokeRE GitHub. So if you want to check out the source code, and then it'll basically look for the basic block containing slice byte to string. And then once it does that, then it'll acquire, let's see, cross references. This should be in here. Get obfuscation start, recursive check, recursive call sites. Yeah, so the binary Ninja Python API is really nice because you can just do like get callers with a specific address. And then once I get all of the call sites, then I basically walk the basic blocks, like I mentioned earlier, to find the start of the obfuscation sequences. And then I have various heuristics to look for those given obfuscation sequences. So again, kind of doing these parameter matches, and this is all using the binary Ninja Python API and looking for specific instruction tokens, etc. So it might look kind of complicated, but it's actually not super complicated. It was pretty hard to find reliable instruction sequences to, one, find runtime slice byte to string, and then two, finding the start of the obfuscation sequences. But it works pretty good. So I'll show you a demo of that right now. So we'll use our test binary, and then I'm going to open up a real piece of malware that we can test on. So I have this plugin. So if I click on Ungarble pane, this is basically the extent of the plugin. If I click on get target locations, basically it's going to do those heuristics that I was talking about earlier in order to find the slice byte to string location. So here it already identified those. Or here it identified this address as being slice byte to string, which I already labeled here. So it successfully found that using those heuristics. And then here on the right-hand side, within Garble, you can click on these addresses and it'll take you to the obfuscated sequence address, which is pretty nice quality of life stuff. And then if you right click on any of these entries and click Ungarble string, then it'll recover that string for you. So not really sure what this 190734 is, but if I click on Ungarble locations, then it'll attempt to basically recover all of the strings in those given areas. So as you can see, this is just like a stripped down binary. So there's just like, I guess this would be part of the Golang standard library. I don't really know why it has time information in here. But you can see like sync, unlock, mutex, and more time stuff for some reason. Again, not entirely sure why, but you can see like reg create key. So this is stuff that would be in the Windows standard library in compiled Golang binaries, etc. So if I open up a real piece of malware, then we can see kind of a cooler example. So this is a piece of ransomware. And then if I open up Ungarble on here, then I'm going to get those locations again. And so it identified like 1,600 call sites that's currently enumerating. And then again, I can do things like Ungarble string.
Nice.
And then we get a whole bunch of stuff. And then we can start to see actual useful stuff. So cha-cha-20. So this could indicate, okay, this binary might be using a cha-cha-20 library, which would make sense if it was ransomware. And if I do Ungarble locations, then we can see we get a whole bunch of different stuff. So they have, I'll just wait for this to finish. So it's currently ungarbling 800 locations within the binary. And once we're able to identify some of these strings, so as you can see, it doesn't work perfectly in all scenarios. Like this might be false positive. But we can see, okay, they're probably using JSON. Okay, they're probably using hex encoding. Let's see if we can keep going here. Adjust token privilege, like that's pretty standard for malware to use, so it can adjust its privileges for various tokens in their embedded process to do various operations, usually security permissions related. let's keep going. And then the nice part about having the start and end address on the left hand side here is then you can just navigate to any place that this is used. So let's see. I think there's interesting stuff later on. So yeah, like tile wallpaper. So a lot of the times ransomware will actually set a wallpaper on a given desktop to indicate that the system has been encrypted. Unable to get language. So a lot of the times, a lot of malware will check the language on a given system. Unable to lock file. Like this is all stuff related to ransomware. So yeah, that's basically the demo. I know it's not super crazy, but once you can recover these strings, especially for a lot of these embedded libraries, then it makes it a lot easier for being like, okay, I can ignore this area of the code because it is a Golang standard library, or okay, this is actually strings related to the malware itself in the case of malware. So I can focus on those areas of the code and what's being called from there, etc. And then once you can identify all of the areas that you're interested in, then you can mark up the reverse engineering database accordingly. So
yeah, that's really cool. It's a great contribution to the community. So that's awesome.
Yeah. Any other questions?
Not too much has popped up. I got one question. Someone's asking, would you have been able to write Ungarble without the source code to Garble? And are you seeing much in the way of custom obfuscators?
Yeah, that's a great question. So yeah, so a lot of people might be like, it's open source. Why do you have to reverse engineer? So I would definitely have been able to, but it probably would have taken me a lot longer. So if I'm looking at custom obfuscators, then I'll look for those types of obfuscation sequences that are occurring again and again. And if I'm able to identify those obfuscation sequences that are recurring, then I can write similar type of tooling without knowing how the actual source code works. And there's definitely like thousands of custom obfuscators that are used by malware authors all the time. And then basically you have to look at the code itself in something like Binary Ninja or IDA in order to determine if there's any potential patterns, etc. And then there's even libraries that will attempt to identify those obfuscated areas for you. So actually, I was just reading. So Mr. Phaser.
Peter's asking, is this already available in the Binary Ninja plugins manager?
No, I'm going to clean up the code and then I will be submitting it to the Binary Ninja plugin manager. But sorry for the delay. I've been kind of heads down with a bunch of stuff, but yeah, that's next on my to-do. So it should be soon. So keep an eye out for it.
And you start getting issues being opened up, right?
yeah, exactly. This doesn't work. Okay, yeah. So this is a really good example of a plugin for Binary Ninja from Mr. Phaser. So Tim Blizzetko is a very famous security researcher, and he does a whole bunch of different trainings, etc. So definitely check out this plugin because it has a bunch of automated techniques for identifying various forms of obfuscation in Binary Ninja. So not only can you look for these patterns yourself, like I mentioned, but you can also use these automated techniques in order to see if they're recurring throughout the binary, etc.
Someone's asking a more high-level question. Do you often see the need to do code analysis, or is behavioral analysis usually enough?
Typically, I'll end up doing code analysis simply because there's sometimes there's techniques that are being used to prevent the behavioral analysis, so dynamic analysis, and those can actually prevent you from seeing all of the execution paths within the malware, or it can be doing only certain execution paths on a given version of Windows or whatever. So more often than not, I'll usually end up doing a static analysis or the code level analysis.
Are there any things specific to Go around like anti-debugging, anti-reversing that are not like just the general stuff with all languages?
I actually haven't seen a ton of Go anti-analysis stuff, but I do think I think I have seen the standard like performing certain instructions to see if it's in a virtual environment, checking for certain usernames and computer names that are often used in sandbox environments and stuff like that. But I don't think there's, but like those are used in everything. So I don't think I've seen anything unique to Go.
Cool. Awesome. I don't think there's any more questions. That was really great, though. Thank you so much for coming on. I think definitely a lot of people got some value out of this one. It'll be up on YouTube, of course, in its full length. Any parting words, Josh?
No, thanks so much for having me. If you want to check out InvokeRE, just invokere.com. And thanks so much for having me. It was awesome.
Yeah, and I'll post all the links again in the YouTube description that I've been displaying on the screen as we've been going. But again, great contribution, and thank you so much, and love to have you on again in the future.
Sounds great. Take care.
Josh, bye-bye, everyone.